Hi, welcome back. So last time we finished up looking at kinematics in one dimension. So we were looking at problems where we had something maybe accelerating in the x direction, or maybe something accelerating in the y direction, but we didn't mix them up. It was only x or only y. What we're going to do now is start looking at kinematics in two dimensions, and this brings us to our next section, section 3. So how are we going to deal with that? How are we going to deal with motion that actually could be moving in the x direction and in the y direction at the same time? Well, there's a very, very important thing that we're going to that we'll realize that will simplify these problems. First, just imagine that I toss this object, this apple, up and down. We see that it goes up and down, and we know the acceleration from Galileo's law of falling bodies. We know the acceleration is always downward. It slows down as it moves up, and then it speeds up as it comes down. Well, what if we combine this motion with a motion in the x direction as well? So imagine that I'm walking in this direction, and I throw this ball up like this. So I'm moving in x, and the ball goes up and down in y. Well, notice that it's still moving in the same rate in the x direction. The x motion is still a uniform motion in the x direction, while we then just have this y motion kind of on top of, I'm not throwing it straight up and down very well, the y motion kind of in the same, along with the horizontal motion at the same time. So let's do that. All I'm going to do is I'm going to toss it up and down like this, but I'm going to be moving horizontally at the same time. So we know basically, or we can see, that we can separate those two motions. We can separate the uniform horizontal motion, and then we can separate the vertical motion. You might try this the next time you're in a car that's going down the road. Not if you're driving, but if you're in the back, hopefully you don't hit your driver on the head with your object or whatever. Next time you're driving in a car, or you're in a car, being driven, and you're going at a steady rate, you might just try and toss something up and down like this. And you can notice that, well, it goes up and down just as though you were standing still. But you know that it's moving down the road, so you know the actual motion is something much more complicated like this. But to you, you can basically just look at the vertical motion with while you're ignoring the horizontal motion. Well, that's going to be a great advantage to us when we try to solve these motions with the kinematic equations. With one-dimensional motion, we had the 4 kinematic equations that we looked at problems last time. Well, what about with 2 dimensions? Well, we'll have 4 equations for the x motion, 4 equations for the y motion. Let's write those down and just take a look at them. With 2-dimensional motion, we now have 4 equations to describe the x motion, and 4 equations to describe the y motion. Now there's a couple differences between the equations. Well, first we have x is over here, y is over here, that's obvious. But also notice that over here, for example, instead of just v, the final velocity, this is v sub x. That means that's the x component of the final velocity v. And then v naught sub x, that's the x component of the initial velocity. So for any of these vectors, like the position, say the position vector r, which is now in 2 dimensions, so we might have, say, an initial position vector r. So here's our initial position vector r. We break that down into components, so the initial x component will be x naught, the initial y component is y naught. So this would be the initial position of our object, wherever that is relative to our origin. So here's our origin. And then imagine perhaps we've got some initial velocity vector. So however this thing is, wherever it is, it's moving with some initial velocity vector. We'd have to break that down into components, an x and a y component. The initial x component is v naught x, which is in here. The initial y component, v naught y, which is in here. So we have to take all these vectors, like the initial position, the final position, initial velocity, final velocity, acceleration, find the components of those things, and then those components are what go into the different equations. Okay, great. Well, with now twice as many equations, we might think we have twice as many variables, and we almost have twice as many variables. Rather than now just x naught x, we have x naught x, y naught y. So we have two initial variables with two initial position variables, two final position variables. What about the velocities? Well, now we have v naught x, vx, initial velocity component x, final x component of the velocity, but then we have v naught y and vy. So two initial velocity components, two final velocity components. And then we have ax, ay, acceleration component of x, acceleration component y. So those are twice as many so far, but then we only have one time variable. T is the same for the x motion as the y motion. So that fact that we don't have two time variables, but only one, means that we don't have quite as many variables as twice as many. We have one less than twice. So we had 6 variables with a one-dimensional motion. We'll have 6 plus 5, or 11 variables for two-dimensional motion. All right, excellent. Now, what we're going to do basically for the rest of this lecture, and then also the next one, is look at some examples of applying these equations to different two-dimensional motion. Two-dimensional motion problem. Okay, well, let's get started. Here's the problem. Dr. Evil throws a ball horizontally at 20 meters per second from a height of 1.50 meters. How far will it travel horizontally before it hits the ground? And we are to ignore air resistance. First, Dr. Evil is a friend of mine, and he kind of helped me out with my classes, throwing balls and flying rocket ships and things like that. So both in 1111 and 1112, he shows up in a lot of these problems. Now, 20 meters per second, that's pretty fast. Dr. Evil's got a very good arm. All right, so what's the first thing we do? How do we go about solving this problem? Many times my students say they don't know how to start a problem. The first thing to do is let's draw a diagram. That helps us get a visual picture in our mind of what's going on in this problem. It's really important to get an idea of what's happening. We've got someone who's throwing an object, but not throwing it up or throwing it down, throwing it horizontally. So it's being thrown so that the initial velocity is horizontal from a height of 1.50 meters. So 1.50 meters above the ground, Dr. Evil is throwing this ball horizontally. So let's draw a little picture of that. It doesn't matter if you are not a good artist or anything like that. I am definitely not a good artist. Let's draw a picture. So here we go. Here's the ground. Here's Dr. Evil. Here's the ball. It's being thrown horizontally. So there it is, horizontally. We'll put this speed of 20 meters per second in there. It's 1.50 meters above the ground, so we'll say, okay, well that's 1.50 meters. We're trying to put as much information from the statement of the problem into our diagram, just so we'll be able to remember that and see it very, very quickly. Then the question is, how far will it travel horizontally before it hits the ground? Well, very qualitatively, let's draw in what we think the motion is going to look like. Someone throws a ball horizontally. What's it going to do? Well, it's going to travel horizontally and then come down as it gets closer to the ground. So it's going to come over like this and come down and hit the ground, say, over here. There we go. Let me extend my ground over there. Okay, so there, it hits the ground. Now let's keep in mind, all of these problems, all of these equations, the kinematic equations, deal with two different points. There's an initial point. The initial positions are x naught, y naught, with initial velocity of v naught x, v naught y. Those talk about the initial position, where the object is starting off in the problem. And then there's the final position. Where is the object ending up at the end of the problem? That's the final positions are x, y, and the final velocity components are vx, vy. So we've got an initial position, a final position. And then throughout the entire motion, we've got an acceleration. The components are ax, ay, so the acceleration is uniform. Remember, this whole situation started out by looking at uniformly accelerated motion. So we are assuming that the acceleration is constant for the entire motion. And then t tells us how much time takes place between the initial position and the final position. So let's keep track of what those variables mean. So where's our initial position in this problem? Well, the initial position is right here. This is our initial position, where the ball is thrown. We know some information about the initial situation. We know some information about the final situation. And we can use those to calculate things that we are not given, that we don't know. So here's our initial position. Where's the final position? Well, we're looking for how far it travels before it hits the ground. So over here where it hits the ground, that's the final position, over there. Now, some people might say, oh, well, it hits the ground and it stops, so the final velocity must be 0. But we've got to be a little bit careful about this. Remember, we're talking about uniformly accelerated motion. So these equations that we had only deal with that part of the motion where the acceleration is uniform. When the object hits the ground, we have a different acceleration. The object is going to accelerate differently than just as if it were in free fall. So once it touches the ground, the acceleration changes. So this final position we need to imagine is just before the object hits the ground, just when it's a hair's breadth above touching the ground. That's really what we mean by the final position. We can assume that it's just barely touching the ground, but we're assuming that we're not looking at the point once it rolls to a stop and doesn't move anymore. We are assuming that the acceleration is uniform all the way to the point where just as it touches the ground. We can assume that the acceleration is only the acceleration due to gravity because we're told we're supposed to ignore air resistance. And we're always going to be doing that for any of these projectile problems. Projectile problems basically mean the motion of something as it flies through the air. We're always, in this course, going to assume that we are neglecting air resistance. Taking that into account is a more difficult problem, something that you would do if you were to take a later course in mechanics or something like that, a higher level physics course, but we're not going to deal with that right now. We're just going to assume that there's no air resistance. All right, there we go. Here's our picture. Here's our initial position, our final position. Now what do? Write down the variables. Let's write down all of our variables. If you'll remember, for a one-dimensional problem, what were they? There were 6 of them, and we always wrote them in the same order. Why do we do that? Just to get them kind of into our head. It helps us remember them. And the easier that we can remember them, the easier it will be to write them down to solve a problem. If you always do it the same way, it will just kind of get that into your memory a little bit easier. We're going to do the same thing for two-dimensional problems. With one-dimensional, what did we have? X naught x, v naught v, a, t. With a two-dimensional problem, we'll write down the x variables, then we'll write down the y variables, and then t at the very end. So let's write them down. So for the x motion, what are they? X naught x. Then, not v, we have to put down the x components. So v naught x, v x. V naught x, v x. And then, not just a, but the x component, a x. A sub x. Then we're going to write down the y variables, exactly like the x, but with a y instead of the x. Y naught y, v naught y, vy, ay, and then finally t. There we go. Before we can write down the values for the variables, we have to choose a position for our origin. Now, what does all of this mean? This is the same sort of thing we did with a one-dimensional problem, but what's going on? The idea is, imagine that you have a great big piece of graph paper. So with an x and y coordinates. You're going to take this graph paper and you're going to put it onto your problem so that you can use the coordinates on your graph paper to determine positions on the problem. Well, we can put the graph paper any way we want. We can put the origin down here, we could put it up here, we could put it over here, we could put it down here. We could put our graph paper any way we want. We're just using it to help solve the problem. It doesn't affect the physics of the problem, so to speak. What the ball is going to do is not dependent on where we think about having our graph paper. So we can put it anywhere we want, so let's choose it somewhere that will make it easier to solve the problem. Well, let's take our origin and let's just put it over here directly below the initial position of the ball, and we'll put it level with the ground. So y is going to be perfectly straight up and down, x will be our horizontal coordinate, and our origin will be directly below the initial point, the initial position of the ball. Why? Well, it'll turn out that it'll make it a little bit easier to solve the problem. You can do it somewhere else, and we'll see why it works out well this way. So just imagine we've got this great big piece of graph paper, and here are our coordinates. We've got our x-axis going this way, y-axis going this way. Okay, so there we go. Here's our axes. This is the x-coordinate. That's the y-coordinate. Now let's look at our variables and see what values do we know, what values do we not know, and what values or value are we looking for? What is the question actually asking us to solve for? Well, let's look at each one. Let's start out with x naught and y naught. Let's remember, x naught and y naught, those are the coordinates of the initial position. Where is the initial position? The initial position is right here. Well, we notice the initial position is right on the y-axis. What is the x-coordinate of any point on the y-axis? X is 0. So we know x naught must be 0. What is y naught? Well, y naught is the distance from the origin up to the initial position. But we know that that's 1.50 meters. We were given that in the problem. So we know that y naught is 1.50 meters. Excellent. Now, what about x and y? Those are the x and y coordinates of the final position. The final position is over here, which we notice is on the ground, in other words, is on the x-axis. What is the y-coordinate of any point on the x-axis? It's 0. So we know that y must be 0. What about x? In other words, how far is this point from our origin? Well, we don't know. But notice that is exactly what we're looking for. That's what we want. That's what the problem is asking us for. So we know at the end of the problem, what we want to try and find is our value for x. What is x? All right, v naught x, v naught y. Those are the x and y components of the initial velocity. But we are told the initial velocity is horizontal. It's being thrown horizontally. So we have a vector, and I'm just going to redraw it down here. Here is our initial velocity, and we know it has a length of 20 meters per second. Now, this vector, we want to determine what are the components, the x and y components of this vector. Well, remember, the vector we can redraw. Let's just bring our axes down here. It doesn't matter where our axes are for a vector, as long as we're just looking for the components. We can find the components then by just imagining it's along the x-axis. Well, what are the components of a vector that point right along the x-axis? Well, the y component is 0. We know that there is no vertical component to our initial velocity, so we know that v sub y must be 0. What about v sub x? Well, this vector we know is 20 meters long, so the x component of this must be 20 meters per second. It's 20 meters per second long. So we know that v naught x is 20 meters per second. So hopefully, for those of you actually in my class, you've done all those homeworks in the beginning of the class that had you find components of vectors. Well, remember, any vector that's pointing right along the x-axis is going to have a 0 y component, and the x component will be just whatever that length is. So we have that v naught x is 20 meters per second, v naught y is 0. Now what about vx and vy? The x and y components of v, which is the final velocity. Well, the final velocity over here, we know that when the ball is coming down to the ground, it's heading downward at an angle. So what are those components? Well, we don't know. We don't know what those components are. We're not sure how the ball is actually moving just as it comes to the ground. So we don't know Vx nor Vy. So we'll just leave those blank. Now what about Ax and Ay? Well, let's remember, for any object that is flying through the air, as long as we can ignore air resistance, what's the acceleration of that object? Well, the acceleration is downward with a magnitude of 9.80 meters per second squared. So our acceleration vector looks like this. It's straight down with a length of 9.80 meters per second squared. So what are the components of that vector? Again, let's put our axes over here at the end of our vector. That vector is pointing straight down in the vertical direction, so what's the x component of that vector? Well, the x component of that has to be 0. So we know that a sub x is 0. The y component of a vector that's pointing down is negative. And we know the length is 9.80 meters per second squared, so the y component is negative 9.80 meters per second squared. So a sub y, negative 9.80 meters per second squared. There we go. And what about t? What is t? How much time does this motion take? Well, we don't know. There's nothing given in the problem that tells us that, so we don't know what t is. Excellent. There we go. There are our variables. Just to make sure, you might go back and check each one and make sure that you got everything correct, that everything you put in there is correct from the statement of the problem. Everything you didn't put in there is something that we don't know, and we figured out what we're looking for. So now what do? How do we solve this problem? Well, we go back to the equations and we try and find what we're looking for. Remember, how do we find something, how do we find an unknown that we're looking for? We have to have two requirements. We need to have an equation that has that quantity in it. So we need to find an equation that has an x in it. And in order to solve for that, we then need to know everything else in that equation other than what we're looking for. So you need an equation that contains what you're looking for in it, and you need to know everything else. You need to know values for all of the other variables in that equation in order to solve for it. Well, I'll leave it to you to look at those equations for a minute and think about how you can solve that. So look at those 8 equations and see if you can find an equation with an x in it. Now, x, not like sub x, v sub x. You're not looking for that x. You're looking for actually the x variable. See if you can find an equation with an x in it where you know everything else. Take a minute and do that. Why don't you can stop the video and see if you can do that and see if you can solve that. I'll take a break and write up those equations.